There we go. All right, so welcome to this class, which is continuum mechanics. So due to the COVID, everything might be a little bit different, but I'm sure we can work it out. All right. So this will be AE/ME 548. Oh, I think that will help. Let me pause over here. All right, so this is AE/ME 548, which is a continuum or introduction to continuum mechanics. Okay, and this will be lecture 1. Okay, so let's give a general definition of continuum mechanics. So continuum mechanics is all about using linear algebra and calculus. So that's why it's almost like a mathematical class, linear algebra and calculus, to describe the deformation and when we say deformation, we need to think about strain, which is related to the deformation, in bodies, so in solid bodies, but also in fluids. Okay, so basically this class is about putting down the foundation, understanding the foundation behind the equation you study in solid mechanics for structures, or the equation you use in fluid mechanics and so on, okay? So it's to relate the deformation can be of a solid or a fluid, okay? And we relate them to the constitutive equation which basically will be the fundamentals equation that dictate, let's say for example, for structures will be what? If you want Hooke's law, something like that, for bodies, solid bodies, and for fluid, what is the equation? What is the only difference really between solid mechanics and fluid mechanics? Is that in one, you're going to relate the deformation strain to the material through the Young's modulus, no? Defining the stress. But for the fluid, what do you define? We'll have the viscosity times the velocity profile, no? Okay, these will be the two constitutive equations of fundamental equations. All right, and then something that we study, but I'm not going to put it here because something more complicated, but it's also this equation when you go from the deformation to the constitutive equations, you need to satisfy some restraints. So for example, in structures, you can have boundary conditions, can be clamped, can be simply supported, and so on, okay? So this will be different equations to go from the deformation, or to go from the constitutive equation to the deformation or vice versa. And that's type of equation I call compatibility equations, okay? But it will be, that's more into depth, okay? The compatibility equation basically are there to define that a structure deforms nicely. So for example, let's say you have a square, let's say of a square made of different parts 1, 2, 3, 4 is that once it's deformed, those four members stay connected. No, you know, that will become unconnected. So in order for that to happen, the equation must satisfy the compatibility equation. Okay. All right. So we talk about the constitutive equations. Then we can move a little bit more. Let's talk a bit more about constitutive equations. So let's say here we have for constitutive equation, this is important. This is really what the whole class is about, okay? To come up at the end of the class, we'll be doing this. So for example, for solid bodies, we say you have the stress equal to the Young's modulus times the strain. So we just say over here that the strain will be related to the deformation. Okay, this is the Young's modulus, which is also the modulus of elasticity. This one will be related to what? To the material. Okay, and that's why if you have a beam made of wood or steel, the stress will be different. Okay, and that will be now the stress. So this is the constitutive equation. So obviously here, this is a simple case for an isotropic material, but you might have materials like composite, no, that can be orthotropic and so on. So all this equation here takes another shape, no? This is only one component, but if you have orthotropic, you have 3 components. I think this one will be a matrix of 9 different components, okay? If you have 2 axes of symmetry, I think it's 18, and then you can have up to 81 if you go to the completely without any axis of symmetry. All right. So this will be for solids, okay, for solid bodies. Now, if we have fluids, what is the constitutive equation for fluid? Is tau. I think here I put the dynamic viscosity, but sometimes it's also used mu. It doesn't matter which one you use. Delta U. Let me change here. This is the velocity profile, so it should be delta T. Should be a T over here. Where here the velocity profile. I'm sure that from fluid, you always remember what is this condition here. This is the no slip condition, no? Okay? And from the no slip condition, you start deriving all the equations. And you assume that at this point, this is 0. Maybe I could do another figure, small figure here for this one. If you do the figure of the stress and strain, that relates the Young's modulus, you end up with a straight line. So this is the shear stress. So again, is the stress. This will be the velocity profile, which is related to the deformation.
So the vertical axis is T, right?
The what?
The vertical axis is T.
The
With respect to which you are differentiating.
in this one here?
Yeah.
I mean, this is just a height. So this will be distance, and this will be just the height of the layer, of the shear layer. Can be y, yeah, can be x. This could be x and y, but this would be the changing function of time. Okay. This is like the shear layer. Will be 0 over here as you go up. Okay. And this will be here. This doesn't matter if it's a dynamic or kinematic viscosity. This is just the viscosity. But again, this will be the one relating the equation to the different fluids. Okay. The same thing we have the E to the different material. This will be the one for the different fluids. Okay. All right. So now, something we need to do as well is to define what is really, because that is what is confusing about this class, is that if I ask you somebody, what is a continuum? So a continuum, that's what makes this class different than the other ones, okay? So a continuum model. And here's everything a matter of how deep or how much detail you want to study the problem, okay? So imagine that you have water. Let's try to take an example, water. So water, if you want to study water, what can you do? You can study water at which is at the continuum level. That would be just to study liquid water. That would be this would be really the continuum, okay? Because if you just look at the water itself, that's liquid water, more or less the properties will be constant throughout, no? But now, what happened if you decide to say, okay, no, I'm going to look at the water from a more chemical point of view. Now it's H2O, no? So let's say I attach 2 molecules of hydrogen to a molecule of oxygen. Now, does that really become a continuum medium? No, you're looking now just at the molecules, no? So at this level, that's not at this level that we're studying the equation. We're studying the equation, fundamental equations over here. If you want to study what happens at this level, you will have to define different equations, no? Okay? And if you want, you can go even deeper, and you could go to say that you could study this at the atomic level. So you know that this will have 3 different orbits. This will be the nucleus over here. That this will be the molecule oxygen that on the outside will be connected to oxygens. But you know that the valence of oxygen is actually 6, no? For outside, you might remember that or not. But only 2 will be connected. If you wanted to connect more, you could connect them here to the other ones, no? But again, that's not the important part over here. It's just to see that depending on what scale you want to study the problem, the equation will be different, okay? So when we say continuum, it's at this level over here. So for liquid will be liquid water. If you look at the solid medium, will be the one you can touch. You're not going to start looking at the microscopic properties or even smaller, okay? You want to keep it at the medium, at the continuum medium. All right. So next, we're going to look at the essential mathematics that are used in basically continuum mechanics. So essential mathematics. Okay, so just like I said before, the main thing in continuum mechanics is to use linear algebra and calculus in order to define the problems, no? So I'm just going to say the main language of continuum mechanics is linear algebra and calculus. And in calculus, it will be a lot more tensors, okay? So the first thing in calculus that we're going to define is vectors. and tensors. So if you did take your ME 501, which is modeling methods, you will be familiar with this, but I need to do a review for the AE students, okay? So basically here I'm going to do two columns. This is pretty simple. It's just a matter of notation. We can divide this in two. All right, so imagine that you have here the current system, X, Y, Z, that will have as unit vector I, J, and K. Okay, so if we move that to some type of initial notation to simplify, to simplify everything in the notation, this could be X1, X2, X3, and this could be then unit vector 1, unit vector 2, unit vector 3. Okay, so now if we want to define a vector in this coordinate system, what will you have? You have here, let's say, P, this will be the vector. And this point P here might have, oops, this should be straight over here. I have one component on this coordinate system and one on this one. So this will be our vector, let's say U bar. And if we need to look at the angles, it will be alpha X, alpha Y, and this will be alpha Z. But if we do the same figure using the initial notation, I mean, it will be the same figure again. But this time the angles will be alpha 1, alpha 2, alpha 3. Okay, so you need to write the vector. You have here u equal to ux I plus uy j plus uz k. Where your ux will be equal to what? U cosine alpha x, uy will be u cosine alpha y, and uz will be u cosine alpha z. This is what is known as the directional cosines. So at the end, you will just have u here, vector u, will be equal to ux, uy, uz. Okay, you need to write it down. So again, here, this is kind of similar. If you do it with initial notation, we'll have what? u1, e1, plus u2, e2, plus u3, e3. And this will be, u1 will be u cosine alpha 1, u2 will be u cosine alpha 2, u3 will be u cosine alpha 3. But this time you could just rewrite this as what? This is what's going to help. If you want to do it long, you have from I equal to 1, 2, 3, because this is 1, 2, 3. U sub I E sub I, no? This would be the same thing as writing this line over here on top, okay? Or you can actually compact model notation and say this is U sub I E sub I. And when the subindex is repeated, you need to do the summation through all of them, okay? So this is what I'm going to write. So you see that this notation can be more compact than this one, okay? So probably from now on, we're going to use this type of notation to derive all the equations. So this will be page, so the previous one was page 1. This will be page 2. Okay. Okay, so let's say the summation convention for the signs. Summation convention. So the summation convention states that in Cartesian coordinates, which we'll be using most of the time, whenever the same subscript occurs twice in a term, that subscript is to given all possible values. 1, 2, 3. And the resultant added together. So basically, if you look at it, is what we did before, okay? In this, I'm going to give more example, but this will be what? U1, E1, U2, E2, U3, E3. Repeat it, you need to give all possible values, no? And then you add them together, okay? And we get the same. All right, but let's say we have here A sub I, A sub I. What would that be? Would be A1, A1, A1 squared, plus A2, A2, plus A3, A3 squared, okay? Now, I mean, here I use I, here we can change the, you could use I, you could use any letter. Let's say AKK would be what? A11 plus A22 plus A33. All right, now let's do something a little bit more complicated. So AJ2 times B3J. So here you need to do what? You're gonna have, so you need to do like 1, 1, no? So you're gonna have A12, B3, 3, 1 plus A 2, 2, B 3, 2 plus A 3, 2, B 3, 3. Okay, so you see this compact notation in this case is 1, 2, 3 times. All right, and let's do one more over here. What would be U sub I, V sub I, Wj, Ej. So this time we have two repeated indexes. So what you need to do here is you need to break it in two parts. So let's first do U sub I and V sub I. So this will give you what? U1, V1 plus U2, V2 plus U3, V3. Obviously, I'm not going to do all of it because I'm just going to do the same thing. And here will be what? W1, E1 plus W2, E2 plus W3, E3. Okay? Okay, I think we're going to do one more. So the one will be, we do, and this is really a tensor, but I mean, I'm just giving an example, but all these are really tensor. Vi E of j. So both of them are being repeated. So this will be equal to what? This will be equal to T. Let's say we do T1 J V1 AJ plus T2J. Here I'm just doing the one, no? You see, I do one by one. I don't want to do both of them at once. It might be too complicated. So T2J plus V2, okay, AJ plus T3J V3 EJ. And now I need to do the J, no? Okay, so I do what? It will be T11 V1 E1 plus T21 V2 E2 plus T3. Yeah. So this would be T11 V1 E1 plus T21 V2 E1, correct? Plus T31 V3 E1. This would be the first term. Plus, now we change the J, will be T12 V1 E2 plus T22 V2 E2 plus T32 V3 E2, and finally we'll have the T13 V1 E3 plus T23 V2 E3 plus T33 V3 E3. Okay, so if you go slow, it's not difficult, okay? But if you try to do all of them at once, sometimes you can get confused. All right. So let's say now you need to do the addition of vectors. Hold on one second. All right, there we go. So now let's say you want to do the addition. Addition of vectors. So let's say you have a vector W that would be the summation of two vectors, U plus V. So this is again, what is a vector? Vector has magnitude and direction, no? Okay, so you want to think about it. So let's say you have a vector that has three components. So one will be magnitude 1 times direction 1, okay? And this should be equal to what? Ui plus Vi for the summation of the two vectors times the Ei, okay? This is very simple. But again, remember here, because when we do the more complicated stuff, these two terms here represent what? The magnitude. This one will represent the direction, okay? So a vector has magnitude and direction. Okay, so now, similarly, we do the multiplication. So you have two different cases. You can multiply case A by a scalar value. So let's say your scalar is lambda times a vector V. This will be equal to lambda V of I, E of I. And the other one, let's say, will be the dot product. So what's the definition of the dot product? Is U dot V, that's what they call it, the dot product. But mathematically speaking, this is equal to what? The magnitude of U times magnitude of V times cosine of the angle between both vectors. So if you do a figure, let's say this is U and this is V. This would be the angle theta. So obviously, if the two vectors are perpendicular to each other, that means that cosine of 90 is 0, no? So then the dot product will be 0, okay? But let's just try to do here a quick example. So if U is equal to 372, and V equal to 123, determine the angle theta between them. I mean, this is very simple again. But again, we start simple, but here everything gets complicated exponentially, okay? Pretty quick. So over here, we use the definition. We have U dot V equal to UV. I'm going to change this a little bit, okay, to make it faster. UV cosine theta. So this will mean what? Cosine theta equal to the dot product, UV, divided by the magnitude, no? The product of the magnitudes, correct? Do you want me to do this? Maybe it will be easier to comprehend. Okay, might be easier. And that way I can, yeah, so that way it would be magnitude. Okay. So what would be the u dot v? So in this case, where u dot v, I mean, you know how to do this, would be what? 372 dot 1, 2, 3. So now when you do the dot product, do you get a vector or do you get a scalar? You're going to get a scalar quantity, no? So what will be the scalar quantity? Here will be 3 times 1 plus 7 times 2 plus 2 times 3. So this will give you a value of 23. 14 plus 6, 20 plus 3, 23. Next, the magnitude of u will be equal to what? So it will be 3 squared plus 7 squared plus 2 squared, which is what? 9 plus 49, okay, plus 4, that will be 62. And v will be 1 squared plus 2 squared plus 3 squared. So 9 plus 4 plus 1, yeah, 14. So maybe I can keep it everything in one page here. So at the end, we're going to have what? So that cos theta here will be equal to what? U dot V, which we know will be equal to 23 divided by the magnitude of both of them. That will be square root of 62 times square root of 14. And if you do the calculation, so you do the calculation, then you do the A cosine, should give you that this is equal to 38.678 degrees. Okay, so that should be this vector over here, the one right here. Okay, all right. Okay, so let's just write the thing we said before because it can be important if u dot v equal uv cos theta. So that means that if u is perpendicular to v, then u dot v is equal to 0. Okay, because we know that cosine of 90 is 0. Okay? Okay, so we know that dot product can be used in order to find the angle between two vectors. Okay? What is the other thing that the dot product is used for? If you remember, I mean, statics, even though I didn't teach it that way, but really statics to me, I always say is a vector course. Okay? Because what you do, you replace the force by a vector. Okay? So the forces have magnitude and direction. So if you want, for example, if you had a force and you wanted to find the magnitude of that force in one direction, what did you have to do? You would take in the vector of the force and you would doing the dot product with the vector giving the direction of whatever direction you wanted to choose, no? Okay? So the second function really of the dot product is to find what is the component or a vector in a certain direction. Okay? In statics, that was called for the forces. All right? So let's do a very quick, simple example for that. So let's say, so for same data as before, so for U equal 372, and V equal 123, determine the component of U bar of U, sorry, so in the direction of V. So if we want to find in the direction of V, what is the first thing we need to find? We need to find what is the unit vector of V. Okay, first thing to do is to find unit vector of V. So now what do you know? V by definition is equal to what? V times a unit vector, no? Let's say EV. So what is the unit vector equal to? Is equal to the vector divided by its magnitude. Okay, everything is calculus over here, okay? So this will be equal to what? If V will be equal to what? 3, 7, oh, sorry, 1, 2, 3 is V. So 1, 2, 3 divided by the magnitude that we calculated before, which is what? Square root of 14. Okay, so basically this is EV, okay? I'm not going to do the calculation. You want to go ahead. But if you want here, it's not going to simplify anything. EV will be equal to 1 over square root of 14 of 1, 2, 3. So now, the component of U in the direction of V will be given by what? So U, you can write it this in this form. U in the direction of V will be equal to U, which is the vector. And we need to dot this one with the unit vector on the V direction. Okay? So what would that give us over here? So what is U? U we say is 372, no? From the top. And the unit vector will be 1 over square root of 14 of 1, 2, 3. So I put the dot product over here. Okay, I don't really have the values for this, but we can kind of do it. No, I don't have the value, so. No, I don't have the value. So if you want to go ahead and do it, so it will be what? It will be 1 over square root of 14. If you want, we can just write it down. Of what? The dot product should give us a scalar, no? Yeah, so it will give us what? 3 plus 14 plus 6. So this will give us, oh, we had before 23 over square root of 14. Okay? So the component of U along the V direction will be 23rd of square root of 14. The application in statics was if you want to find the component of force in one direction, what will you do? You take the force and you multiply, you dot product with the unit vector of that direction. Okay? Okay, we still have about 20 minutes, good. All right, so the next thing that you need to learn, that you already know from vector calculus is what? If you have the dot product, the other one is the cross product. So page 6, we're going to look at we had A, B, and C will be, so we have the scalar product, the dot product, and the third type of multiplication we can have is the cross product. And this one by definition is what? U cross V is equal to the magnitude UV sine of theta, or UV sine theta. Okay, so here imagine we have 3 vectors. So we have U. So let me do U in a different direction. Let's say this would be V, will be easier. This is U. So you do U cross V, then the resulting is another vector that should be perpendicular to the other two. Okay? So what does that mean? So this one tells you 2 vectors are 90 degrees, all right? UV, this will be, so if the vector needs to be, so basically the 2 vectors are perpendicular, all right? The third vector will be perpendicular to the other 2, okay? So what does that imply? If 2 vectors, let's say what is the opposite of perpendicular? Let's say if U, instead of being perpendicular, is parallel to V, then what should be the cross product equal to? Should be equal to 0, no? Okay? So that's it. That's all I wanted to say over here. All right, so let's do an example. So how do you do the calculation? There's 2 ways to do it. I always do it one way, but generally people from India generally do it the first way we're going to do it here. If U equal UX, UY, UZ, and V equal Vx, Vy, Vz. So what would be if we do U cross V, it would be equal to what? I should have used U1, U2, U3, doesn't matter. We use the X, so it will be X I plus UYJ plus UZK cross VXI plus VYJ plus VZK, no? Because a vector has magnitude and direction. So this should give you what? It would be equal to UX Vx times what? I cross I, okay? Which is equal to what? I is parallel, no? They are collinear, so that means that this term will be equal to 0, okay? Plus, let's do the second one, Ux Vy, so this will be I cross J. So let me finish this line and then we look at what is this equal to, plus Ux Vz times I cross K, okay? So I don't know if you use this or not, but basically what does that mean? That if you do I cross I 0, no? But if you do I cross J, that would be equal to what? I cross J yields to K. Okay, so it would be equal to K. And then I cross K's go on the opposite direction, so that should be equal to what? This should be equal to negative J. Okay? And we have three other components over here doing the same. So we have here plus U, Y, dx of J cross I plus Uy, Vy of J cross J plus Ui, Vz of J cross K plus Uz Vx of K cross I plus Uz Vy of K cross J plus Uz Vz of K cross K. So let's do this one. So the J cross I will give you what? Negative K. J cross J 0. J cross K will give you I. K cross I will give you J. K cross J will give you minus I. And K cross K will give you 0. So we can rewrite this as what? We are going to simplify it very, very quick. It's U sub Y Vz. Which one is the I? So I will be U sub Y. Where are the I's? U sub Y Vz, no? I minus Uz Vy. This will be for I. Now for the J, what will you have? Generally, it's not the way it's written, but I'm going to do it this way. The J will give you Uz Vx minus Ux Vz J. And finally, the K component will be Ux Vy minus this one here, which is Uy Vx. And this one gives you the K. Okay, so this is really the way it's done. If you needed to write a computer program, this is really the way it should be done, no? Okay, but to tell the truth, I think I only do it that way when I teach this class. What is the other fastest way to do the cross product? To use the matrix, no? Okay, or or using matrix notation, what do you have? U cross V will be equal to what? The I, J, K, and you put here UX, UY, UZ, and you could put over here VX, VY, VZ. Okay, so Johnny, you do what? You cross the first one now. For the I, you cross this one, so you get what? UY VZ minus UZ VY, and this will be the I component. Now here, this is the only thing which is a little bit different. When you go from one to the other one, you need to switch signs, no? Ordinary value, and now you will have UX VZ minus UZ VX times J. Now you go back to the K, will be positive again, okay? And you're over here, UX VY minus UY VX, and this will be the K. All right, so far, everything pretty simple, no? All right, now let's go, and that will be the last thing. So let's find over here, vector equation of a plane. So we know the basic mathematics, no? So now let's try to apply it. So let's say we have a reference frame. I know I'm still using X, Y, Z, but because it's just easier to understand at this point. But remember that all this stuff should be written X1, X2, X3, no? And let's say we're gonna write down the equation of a plane. I'm gonna do it kind of perpendicular, but just because it's easier for me, but it doesn't have to be perpendicular, okay? So let's say this is the plane. So let's see, how can we find the equation of the plane? Obviously, we need to use something that we have learned. So let me add stuff to the figure. So let's say that we can know that there is a vector n, unit vector n, that is perpendicular to the plane. Okay? So let's say n vector perpendicular to the plane. And now let's say that we have 2 points on the plane, P and Q. So PQ points on the plane. Okay, so if RPQ on the plane, let's say we do the vector RPQ. If we do RPQ now, let's see now another color. this vector will be what? Will be parallel to the plane. Yeah? Okay. So RPQ will be okay, so if that is the case, what does that mean between vector n and the vector RPQ? Both of these two should be perpendicular to each other. If they are perpendicular to each other, what does that mean? If n perpendicular to RPQ, that means what? That n dot RPQ should be equal to 0. Okay? So here, for the sake of simplicity, let me just say that P is equal to X, Y, Z, and Q is equal to X bar, Y bar, Z bar. I think I complicated the notation a little bit. Let me go to the next page, otherwise I'm going to put way too much information here. But if I just rewrite the same equation using the components, so basically I just need to rewrite n dot RPQ equal to 0. So n, let's say n over here, we don't know what it is, but let's say it's equal to n1, n2, n3. So we have what? n1, n2, n3 dot PQ will be equal to what? Will be equal to X bar now minus X, correct or not? Will be coordinate X of Q minus 1 of X. Coordinate Y will be Y bar Y, C bar minus Z equal to 0. You see the simple calculation. So now, what happens if we do this calculation? We get that N1 times X bar minus X plus N2 Y bar minus Y plus N3 Z bar minus Z should be equal to 0. Okay, so this is really the equation of the plane, but you can rewrite it in a different form. You can say that this is equal to N1 X bar. It doesn't matter. You can use X bar or the Y bar. So you can do N1 X bar plus N2 Y bar plus N3 Z bar could be equal to a constant D, where D should be equal to what? Should be equal to these terms, the minus X that went to the other side, no? Would be equal to N1X plus N2Y plus N3Z. So this is the equation of a plane. Okay, so now if I give you 2 points, you can find what is the plane that goes through those 2 points, no? Okay, so why are we doing all that stuff? Okay, let me try to give you an idea, because if you think about stresses, okay, you have a structure that is subjected to stresses, And now somebody tells you need to find the stresses along a cut. You make a cut on the plane, no? How are you going to find the stresses on that plane? You first need to find what is the equation of the plane, correct? You find out what is the direction of the plane and you multiply that by the stress. That will give you the quantity of the stress on that plane. Yeah? But if you don't know how to find the plane, how to make the cut, there is no way for you to find the stresses on that plane. Does that make sense or no? Okay? All right, so we stop over here for today.